All right, we are going under the hood of one of the most talked about technologies out there. But we're not just going to talk about a generative pre-trained transformer or GPT. Oh no, we are going to build one right here from scratch. I mean, you've probably used an AI like ChatGPT, right? And it's kind of mind-blowing. But have you ever just stopped and wondered what is really going on inside that black box? How does it come up with that stuff? Is it some kind of digital magic, or is it something we can actually understand? Well, here's the good news. It's not magic, it's engineering. It's a specific blueprint and architecture that's carefully put together from some core, pretty understandable ideas. And once you see that blueprint, the magic starts to look a lot more like clever construction. So that is our mission today. We're going to build a small GPT model together, piece by piece. Think of it like a really complex Lego set. We're going to start with the basic bricks, figure out what each one does, and then snap them together to create something pretty incredible. You ready? Let's get building. Okay, first things first, what are we even trying to build? At its very core, a GPT is a prediction machine. You feed it some text, and its entire job, its only job, is to predict the most likely next word. Then it takes that new word, adds it to the input, and does it again and again. That's the whole game. Simple, right? So, to build a model that can do that, and one with lots of layers, we have to solve a few key engineering puzzles first. And here's puzzle number one. When you stack dozens of these network layers on top of each other, the training can get incredibly unstable. The numbers flowing through can either shrink down to almost nothing or just explode into chaos. Either way, the model can't learn a thing. So, how do you keep the whole thing on the rails? The solution is a really brilliant and simple trick called layer normalization. It's like putting a little regulator on every single layer. It takes all the outputs and just mathematically rescales them, forcing their average value to be 0 and keeping them from spreading out too much. This keeps the signals in a nice, healthy range, which makes the entire training process way more stable and reliable. Okay, next puzzle. You ever play the game of telephone? You know, where you whisper a message down a long line of people? By the time it gets to the end, it's just total nonsense. Well, the same thing happens in a deep network. As information passes through layer after layer, the original signal can get weaker and weaker. It's a classic problem called the vanishing gradient. So how do you make sure the important stuff from the beginning doesn't just get lost? You build an express lane. These are called shortcut connections, or sometimes skip connections. The idea is wonderfully simple. You just take the input going into a processing block and add it directly to the output. This creates a second, shorter path for the information to travel, making sure that original signal is never totally lost. It's absolutely crucial for training these really deep models. Now, inside each of our main building blocks, there's a little engine that does the real computational heavy lifting. It's a pretty simple two-layer feed-forward neural network. Its job is to process the information at each spot in the sequence, all by itself. And that little network uses a special kind of on-off switch called an activation function. A lot of older networks used ReLU, there on the right, which is super simple. It just cuts off anything negative. But GPT models use GLU on the left. See that smoother curve? That little bit of nuance, especially for negative values, allows for more subtle adjustments during learning. And when you're dealing with something as complex as language, that subtlety is a huge advantage. All right, we've got our components, we have layer normalization, shortcut connections, and that feed-forward network. Now it's time to assemble them, along with one other critical piece called the multi-head attention module, into our ultimate Lego piece, the transformer block. So here's how it all fits together. An input comes in and first gets normalized. Then it goes into that multi-head attention part, which helps the model weigh the importance of different words in the sentence. After that, we use a shortcut connection to add the original input back in. Then we repeat the pattern, another layer normalization followed by that feed-forward network to do the heavy thinking, and finally, one last shortcut connection. This whole sequence, that's one single powerful transformer block. So now that we've perfected our main building block, we're not just going to build a house with it. No, we're going to build a skyscraper. This is it. This is our core, repeatable unit. And the real genius of the transformer architecture is that you can just stack these things as high as you want to create more and more powerful models. And that's exactly what we're going to do. For the small version of the GP2 model that we're building, we take that one block and we stack it 12 times, one right on top of the other. The output of the first block becomes the input for the second, and so on, all the way up the stack. Stacking those 12 blocks, along with all the other little pieces, results in a model with This many trainable parameters, just over 124 million. So what even is a parameter? Well, you can think of each one as a tiny little dial or a knob, and the process of training is really just the act of meticulously tuning all 124 million of these dials, making tiny adjustments over and over and over again until the model gets incredibly good at predicting the next word. Okay, our architecture is complete. We have a 124 million parameter GPT model sitting on our virtual workbench. So let's fire it up. Let's see what this thing can do. We'll give it a really simple, open-ended prompt to get it started. Hello, I am. This is the moment of truth. Let's see what all our hard work has produced. So what do you think it's going to say? It has the full architecture of a real GPT-2 model. It has 12 transformer blocks, over 124 million parameters. What happens when we ask it to generate the next word? It generates this. Hello, I am feature myman buys whiskey attribute argue. Pure nonsensical gibberish. What on earth went wrong? Did we build it incorrectly? No, absolutely not. We built it perfectly. The reason it's spitting out nonsense is actually the most crucial takeaway here. An architecture is just a blueprint. What we've built is a powerful machine, sure, but all 124 million of its dials are just set to random initial positions. It has the capacity to understand language, but it hasn't learned a single thing yet. And this leaves us with the ultimate cliffhanger. We have successfully constructed the body, the full architecture of a GPT model. But it has no mind. It can't think, it can't reason, it can't even form a coherent sentence. So the big question is, how do we teach it? How do we turn this machine of random numbers into an intelligence that understands language? Well, that, my friends, is the story of training.